Hi, my name's Brendan Buffler, and I have the best job in the world because I get to help scientists and engineers in R&D groups all over the world doing some pretty crazy stuff with computers. I work in the HPC or high performance computing community and have for a few decades now. If you've never heard of it, HPC is a technique really rather than a specific set of technologies. It's used to solve big problems that we can't solve with single computers. It usually involves lots of math. We have a reputation for stressing pretty much all of the design points of the technology we put inside machines. It's not just the CPU, but memory, network, storage, and nowadays a lot more. I've built my share of machines the size of a house, and I have fond memories of standing inside a defense data center where one of my babies ran a floating point algorithm so hot that the power spike took out the breakers for the entire data center. Defense sites usually have people with guns who are a bit twitchy. Anyway, here's the way that we used to do it. Supercomputing in its first version involved throwing absolutely everything at speeding up that processor, all one of them. This is a picture of a Cray 1, probably pretty close to the image you have in your head if I asked you to imagine a supercomputer. It costs tens of millions in today's money. Your iPhone now has about 50,000 times more computing power than this beast. Nevertheless, the science we did with it was amazing. The handful of sites around the world could afford them. That number grew over time, but still the economics of building and buying a big machine like this were really tough. Then in 1994 came a disruption event. A couple of researchers at NASA figured out that they could split an algorithm into parts that could run simultaneously on multiple computers, and they could use a local area network to keep the separate parts in sync with each other. And for a certain class of problems, they could actually build compute infrastructure that could come close to matching the performance of those single large machines, but at a tiny fraction of the cost because they were using commodity machines, the kind of things we were using in offices to write letters and we're starting to use to send emails using modems mostly, but let's not go there. This was quite revolutionary because it meant fusion of computer geekery with some straight up economic pragmatism. PCs get the cheapness from scale economics and mass production. Now, I'm making this sound easy, but the insights that Thomas Sterling and Donnie Becker had were profound. We needed networking, of course, but we also needed a deep understanding of distributed computing concepts. Most of the textbooks on that hadn't been written yet. They also needed communications protocols, so scientific programmers could push messages backwards and forwards between the nodes in the cluster to keep all the parallel parts of the overall algorithm in sync. But they invented something that would change the world, and others joined them in to help them invent the things it needed to scale and be more important. Because that was important, and it was an open system in most respects. So after a few years, Beowulf architecture become a generalized pattern for building large machines. The first one that Tom and Donnie built had 16 cores, one per node. It had a grand total of 256 megs of RAM. That's 16 megabytes per node. And when we strung it together with coaxial cables to connect its 10 megabit network together, it could deliver 60 megaflops, which is about a third of what that big Cray system could do. But that was actually just the prototype. So what you're seeing here, 3 years later, they launched a successor. Which used 120 nodes with Pentium Pros, and it was able to go to 10 gigaflops. Now that's more than 60 times what the Cray 1 could do. I'll call this the era when real scaling was born. Now, a lot of stuff happened in HPC in the next 20 years. By 2017, AWS had been born, and it became quite normal for us to have customers running workloads spanning 1 million cores. Scale has become hyperscale. So we're all used to this now. We often call it cloud scale just without even thinking about it. Now, one of the nice things that comes with scale when you operate in the cloud is that a typical scientist's workload, which might be 32 nodes or 64 nodes, fits pretty neatly into the noise of our overall usage curve. So remember, for every scientist we have using the cloud to do some research, we've got a few hundred gamers, probably thousands of people browsing online shopping catalogs, and certainly several trillion pictures of cats getting swapped. Now, that means that we have enough compute to take the jobs from a job queue and run them much, much sooner over a fixed data, faster than a fixed data center capacity could. Since the cloud is a rental model, you don't own the hardware, you don't have to pay for it when you're not using it. That's our problem to worry about. That might sound like a small thing, but it's a big thing. If you're a scientist waiting for a job to analyze a truckload of data from a sensor before you do your next experiment, you'll get to it sooner and get to that next experiment perhaps today instead of next week. So I want to give you a flavor for why this matters. We have this saying in Amazon that invention requires doing a lot of experiments, accepting that most of them fail, and that's something that's something we can live with if the experiments aren't too expensive. In fact, we can do experiment if we can do experiments cheaper, we'll encourage people to do more experiments. So, and since we place so much of our faith in what is basically the scientific model applied to business, we'll eventually iterate ourselves, to find something that works. So doing all these experiments, learning all the lessons from each one that failed, that's actually what gives us the experience to navigate ultimately to the one that works. And as you can imagine, we're pretty fond of that. So here's an HPC usage graph for one of our R&D groups in Amazon devices. They build things like the Echo devices and Kindles. There's a lot of HPC involved because they simulate an insane number of possibilities, like what happens to an Echo when it lands on the floor when you drop it, what the thermal properties are like when the Echo is left sitting in the sun, and so forth. You can see the two big events on the curve. The meeting with the executives to see if they like the design concept, followed by 44 hours of insane redesign to figure out if the executives' request to change that design could work. Their compute needs surged by about 40 times their usual daily capacity. Now, if they're using a traditional cluster, they'd have had to postpone the meeting by about a month or so. Maybe a month and a half. But they didn't, so they didn't, and they got the answer over a weekend instead. It cost them a trivial amount of money to do this design experiment, and they do this every day now. Scientists do this every day now across the globe. But the job's not done. Anything we can do to lower the cost of failure will expand our possibilities, and not just for people like Amazon devices. Now we move to the locus of the next disruptor. I don't think I need to explain where ARM processors came from or how ubiquitous they are. When I first started playing with ARM processors on Raspberry Pis, I think, they were pretty limited in their math performance. When we built the Graviton 1, we tried it out for some HPC codes, and the results were, let's just say, limited. But the price was amazing. Graviton 2 has changed the game entirely. This is a 64-core processor with some very nice floating point capabilities and some really fast memory architecture. It's also very low cost. So we have something, finally, that, thanks to our partnership with ARM, we manufacture ourselves, can do math really well, has fast memory, and cuts the price of computation almost in half. So I want to show you why all this matters with 3 good examples. Just before we launched Graviton 2, one of my friends, Chris Greenshields, who was one of the inventors of a thing called OpenFOAM, told me that what we used to do on $1 million supercomputer is the stuff we now do for a few bucks an hour on AWS. CFD is the computer simulation of how fluids move around objects. OpenFOAM probably accounts for around half of the world's CPU cycles spent on CFD. In its simplest form, it's not simple, this actually is rocket science. The CFD model puts a 3D mesh on the surface of an object and then calculates the temperature, pressure, and density in all those little boxes in the cells in the mesh. The more cells in the mesh, the better the simulation does in matching reality. The more cells in the mesh, the more math, the more CPUs you need. Lowering the cost of compute has a very big impact. So a rocket company could pocket the savings, but the engineers do what engineers do best. They'll dig deeper. Bigger models, more complex structures, more alternative designs. Chris tells me the customers who are using OpenFOAM in the cloud simulate the airflow around buildings. This means architects can make more considered decisions about how and when to place buildings so they don't cause turbulence effects at the street level where people walk. If you've ever walked through the city of London at all, you've benefited from that. So you might imagine we were pretty happy to find that when we run OpenFOAM codes on Graviton 2, they're consistently 40% cheaper per simulation than the ones running on their big brothers in the x86 world. So expect more interesting buildings and experimental Formula One cards. So these were pretty pleasing results. But we were wondering, CFD has been around for a long time. These algorithms have adapted to exploit every little specialized feature of the x86 instruction set. ARM and Graviton 2 are relative newcomers to this space. So, what was going under the hood that allowed Graviton 2 to go this fast? When we profiled the code to find out what was going on, a great deal of the performance was attributable to the memory architecture. CFD codes stress memory bandwidth like almost no one's business. A few design factors made all the difference. First, the Graviton 2 systems have 8 memory channels per CPU socket compared to 6 on an x86 system, and CFD codes love that. Second, the Graviton systems have only 1 CPU socket per machine compared to 2. This may sound like an odd advantage, but it actually massively simplifies memory handling. Every single core in the machine has symmetric access to every byte of the memory. No tricks are required to juggle the pieces of memory from the far side of the motherboard. And the way this netted out, the Graviton instances sustained a much higher transfer rate compared to their x86 cousins. And that meant CPU cores went faster and spent fewer nanoseconds waiting for data so they could actually get crunching and get more stuff done. Like I said, expect more interesting buildings and strange experimental car designs. Now let's talk about the weather. I'm from London, so best not to actually talk about the actual weather. Let's focus on the simulation of the weather. Weather forecasting works best when it's real time. In fact, if it isn't, it's useless. The faster we can be than real time, and the more accurate we can make these models, the more likely we are to predict the track of a hurricane or a storm. That's important because then we're evacuating the right city on the coast, and we're doing it fast enough to make sure that we can do it well. Weather modeling is kind of like CFD. It involves meshes, they call them grids, and figuring out the basic physics, what goes on in each grid cell. But weather forecasting is on a much different scale of difficulty. There's a lot more physics going on in each grid square than in a CFD model. There's energy being beamed into each cell by the sun. There's insane amounts of turbulence coming from almost every direction. And the size of the landscape over which we're trying to forecast the weather is simply huge compared to a CFD model. For all these reasons and more, weather simulation has been one of the last workloads to move away from traditional, large, custom-designed on-premise architectures. Weather simulation algorithms are also extremely chatty. If you imagine these grid squares mapped onto, say, your hometown, and you imagine weather happening, the action's all around the boundaries between these cells in the grid. When you have great memory bandwidth, then it's easy for one CPU core running the physics on one grid cell to keep the properties of the next cell over in order to figure out what's going to happen next. But if that cell's data is on another computer across the cluster, you need to talk to another computer, grab the data, crunch the numbers. Most likely that other computer is also doing the same thing. We call this a ghost cell exchange. All these ghost cell exchanges mean network traffic. And for a very large weather model, at the scale of a state or a country, the network traffic can be completely insane. CFD has this property too. In most supercomputing centers, we use technologies like InfiniBand to massively improve network performance by massively reducing the travel time for all packets. AWS didn't have that luxury because ripping out our Ethernet would have been an expensive operation. We also didn't want to build an isolated island in the corner of our cloud. We wanted the whole thing to be able to be thrown at a problem. So we invented a new Ethernet-based transport protocol called SRD so that we could release a thing called Elastic Fabric Adapter, or EFA. I'll leave you a link here to chase if you want to know more. The main details worth knowing are that to move millions and millions of packets between pairs of communicating nodes, SRD adopts a kind of swarm strategy where it sprays the packets across multiple simultaneous pathways all at once. This turns out to be a really good idea. Every network in existence experiences packet drops. They're not exceptional, they're normal. And every network that's complex has periodic spots of congestion. Ours is very complex because it's been built up over time and it's huge. So firing packets across a network doesn't work well if you don't take congestion and packet drops into account. SRD does, so EFA works really well. When we run WRF, probably the most popular weather simulation package in the world right now, we see a really nice, strong, consistent scaling curve. And it's exactly, and I mean exactly, the same scaling curve we see on x86, which is where WRF grew up. These are decades, there's decades literally of x86 performance tweaks in there. The math libraries built for x86 contain hand-built assembler routines optimized by Russian mathematicians. The ARM math libraries haven't had that time to catch up. So again, weather simulations at the same speed, but almost at half the price. Now let's talk about stuff much closer to home. Um, and I think we've all been experiencing this. Some of the most important, for me anyway, use cases in HPC reside in using compute to either map and understand the human genome, or to simulate the way potential new drug molecules might bind to cells in our bodies. This is where I think the new disruption will have the most profound impacts, the kind of stuff we all feel the effects from. Human Genome Project is one of the biggest scientific collaborations our species has ever done. It took 14 years of work to map out the first whole human genome. The scientific field had to develop whole new technologies like high-speed sequencers made by companies like Illumina. But when you get output from these sequencers, it's a mess of alphabet soup, like that graphic on the right, in the letters of DNA, A, C, G, T, zillions of them. The output, in fact, looks a lot like someone has put a telephone book through a shredder. Getting a contiguous result that is your whole human actual genome requires a lot of compute to reassemble that phone book from the confetti. Now, it might seem like an impossible task, but there's algorithms for this. Speed matters for the most for the genome assemblies, but not as much as cost. On the cost side, the entire industry has been working to shrink the costs for the whole process. And you can see here that the effort has been wildly successful, beating Moore's law to get the cost to be literally 1% of what it costs to sequence the first batch of human genomes. But the icing on the cake is that the performance is amazing. So not only is the average runtime faster than most of the x86 systems, it's just a notch shy of being half the cost. If you're a country wanting to sequence cancer genomes so that you can design highly customized gene therapies to fight disease, it just got cheaper to do, and you can get the patient on the treatment plan sooner. Finding cancer early, because the diagnostic test cost very little, and you can afford to do more often, saves lives. That's why this matters. Now, the last topic. So we don't walk away thinking that the problem is completely solved. Scientific software is almost defined by its complexity. This tree here shows the dependency relationships between the hundreds of libraries and packages that are needed to run just 33 applications. Porting is hard work. Making sure the results are scientifically valid is crucial. Thousands of details matter. We held a hackathon this year with our friends from the ARM HPC user group and the ARM HPC engineering community, and we managed to pull together 110 people from across the scientific computing community, where the aim was to move a ton of code from the not working on ARM column to the working on ARM column. Now, these people converted pizza into code with the help of a few dozen experts and mentors over the course of a week. And the results they produced were amazing. Just some of the codes that some of these codes haven't been worked on or checked in years. For me, this reinforces why I get up and come to work each day, why I think the cloud can make a difference, and where I think this current disruption has the potential to go. We live in a world where huge numbers of people are benefiting from the work done in the scientific community using computational tools that make the hair stand up on the back of my neck. But the science is hard enough. Some of the tools being used need renovating. If we're to scale the possibilities of what HPC can do, we can't just rely on what CPUs can do in the data centers. We also need to work on scaling the humans who use them. And that means making things a good deal easier to use because the science is hard enough. ARM has been at the front and center of this revolution. The phone in your pocket that you use to talk to the world almost certainly has one inside it. And it's powerful, tens of thousands of times faster than the Cray I showed you earlier. So powerful that sending messages to friends around the globe is second nature. So regardless of the kind of software development you do, what industry you're in, whilst you're here at the Developer Summit this week, think about what you can do to scale the humans who use your code or benefit from the things you create. Making your products just a little easier to use, a little cheaper or faster to run, might be the incremental step that kicks off a revolution somewhere. So I won't say thank you for listening, but, well, thank you for listening anyway. I'll finish this by saying, get busy. Life is short. We have no time to waste. There's a live Q&A session starting now. To join the conversation, take part, join us on Zoom by clicking the yellow button just below the video player on this sessions page.